What we're going to do first is work on your skills with pipetting and spectrophotometry. Make sure you watch the technique videos to help you with this. If you want to do your work accurately and get out quickly, pay attention to pipetting especially. If you're not pipetting correctly, I will make you redo it until time runs out. If you pipette well the first time, you might be out of class an hour before other people who are having problems pipetting. Also, make sure you get comfortable with the spectrophotometry. We'll be doing a lot of spec work in biochemistry. Next time, your lab notebook will start, and we'll do experiment 1, analysis of reducing sugar concentrations. Taking a look at our spectrophotometers, I have some great specs. Each one has a 6-cell holder, holds 1 blank and 5 samples. The light beam of the spec travels left to right. You can flip it 180, it makes no difference. Their path length is 1 centimeter. We're working with semi-micro cuvettes, meaning they're condensed at the bottom, so they don't need as much liquid in them. We're using Beer's law with a path length of 1 centimeter. It needs to be the long direction of the cuvette. If you look at the bottom of the cuvette, that'll be pretty obvious. There's also an arrow on the cuvette, which indicates which direction the light should go through. If you put the cuvette in the wrong orientation, you won't be going through 1 centimeter of liquid, and you won't get accurate results. Taking a look at our cuvette holder, the blank will be in the front. You'll always have a blank in the spec. And then you go on counterclockwise to each position, making sure you put them oriented so that when they rotate to the front, that will also be the path length of 1 centimeter. When you get this, you'll get a graph. You need to graph it before you leave so we can see if you have any data points that need to be redone. So make sure that you show it to us. Your absorbance should increase linearly with increasing concentrations of cobalt chloride. You need to redo any outliers. So if you look at this graph, we have our trend line, we have our equation, y equals 0.01x plus 0.002. Note that it has not been forced through 0, and generally I'll want you to force it through 0. And the student got a very nice R squared. Sometimes you guys get R squareds of 1. If you see a data point that has substantially higher than expected absorbance, maybe you need to mix it again. Don't throw away any samples until we help you if you're having problems. Sometimes, instead of remaking it, literally all you have to do is mix it better with your pipette, read it again. Or it's possible that you get one with a much lower than expected amount of cobalt chloride or any other solution. Perhaps you put it in the wrong orientation. So try checking your orientation, get us to help you if need be. Maybe that is a simple fix. Some of our reactions, the next time we meet, we'll be doing our dinitrose salicylic acid assay. You're going to have to boil the samples for 10 minutes. If you have to remake them, and you also have to wait for them to boil again, it's going to take quite a long time to remake it. So you want to make sure you're accurate. But also, before you get around to that, check your mixing, check your orientation. It's also possible you did not make the reactions correctly. You're going to use your data to construct a standard curve using Excel or Google Suite or whatever you like. What you're trying to do is graph your solutions of known concentration and determine the concentration of your unknown solution. You need to determine the extinction coefficient for cobalt chloride. Basically, when you do the graph, the slope will be your extinction coefficient, simply a proportionality constant that will allow you to determine the concentration of your solution. Then you're going to have the absorbance of your unknown concentration of cobalt chloride, and you'll use Beer's law and your extinction coefficient to determine the concentration. For your graph, you want to make sure you add a title. You label the axes with units. Usually you have scatter plot, add a trend line, equation, R squared. Typically in this class, you'll force your graph through zero, your trend line through zero for your standard curves, not for Lineweaver-Burke. That would just kill your Lineweaver-Burke. For your graph title, which is almost usually the worst part of a graph, think about what you can include that would be very clear on what you're doing. If you're doing a standard curve, you might want to consider the word standard curve in your title. If you're doing a Lineweaver-Burke and you put Lineweaver-Burke in the title, I immediately know that you're working with an enzyme. There's a substrate, a product, you're measuring something in the spec. I know it should have a positive y-intercept and negative x-intercept, that you should have some enzyme present. So that's a lot of information simply from the words Lineweaver-Burke. When you do your title, if you have a reaction, not with cobalt chloride, but with other things we will, substrate, product, enzyme, think about all this information and whether it would be useful to include in your title. Note that there's a graphing help section in the lab manual and on the website. Your worksheet 1 will be due Monday at 10 p.m. to Canvas. The worksheets are in the lab manual and on Canvas. You're going to submit them through Canvas as if they were a quiz. So make sure you complete the worksheets before you go to Canvas to submit them. You'll have 2 attempts to submit the worksheet. So you can go through the questions. If you've got something wrong, you'll find out. You won't know the right answer, but you can try to fix it. And there is a 3-hour time limit for each. So don't sit there working through the worksheet and have Canvas open, or you might time out. Basically, it's going to be set up as a quiz as much as possible on Canvas so that the TAs don't have a lot of grading to do. All right, let's take a look at a couple of graphs before we go. This one, we have absorbance versus alcohol concentration for a title. That gives you no extra information. All you're doing is restating the axes. The x-axis, alcohol concentration, you don't know what alcohol, you don't know what concentration units there are. The y-axis, we know we're measuring the absorbance of something. Is it the alcohol? Can we measure alcohol directly? Often our chemicals cannot be measured directly. We're measuring something else in the spec. What are the units of absorbance? Are they nanometers? No, absorbance has no units. It's measured at a wavelength which has nanometers, but this makes it look like the units are nanometers. The graph there has series on it. That gives you no information. I'd get rid of that. Note there's no equation, no R squared. Also, for this graph, the trend line is added to data that is connected already, making it very difficult to see. And this graph, the trend line is not forced through zero. Typically, but not always, it'll say whether I want you to force it through zero or not. But this one should have been forced through zero and was not. You really don't know that much about this graph. Could be the effect of drinking margaritas on a college student. Higher alcohol concentration, higher absorbance. I don't have much data to indicate that's not what it is. Looking at a better graph, we now have the title, Conversion of Ethanol to Acetaldehyde by Alcohol Dehydrogenase. So we have a substrate, a product, and an enzyme. On the x-axis, you can see our ethanol concentration is measured in millimolar. On the y-axis, we are not measuring ethanol in the spec. We're not measuring acetaldehyde. We're measuring NADH being produced as a result of this reaction, and it's done at 340 nanometers. We have our equation with our y value, and you can see it has been forced through zero. Note that if you're not getting close to zero before you force it, it usually indicates you're not pipetting very well, and that's a clue that you might need to clean up your act. The R squared is close to 1. An R squared of 1 means the data fits the line very well. The closer you are, the better it is. I expect pretty much everyone in the class to get an R squared for this graph of 0.99 or higher. Next week with the DNS assay, it's never quite that clean, but with cobalt chloride, and it should be. Here we have our trend line added, but the data points are not connected. So that's a much better graph. Finally, for safety for this lab, cobalt chloride is toxic and an irritant. You do not need to wear gloves or eye protection. If you do spill the cobalt chloride, wash any affected areas, clean it off the bench. All cobalt chloride waste needs to go into the bottle and the fume hood. And cuvettes are not glass or plastic. They can go into the regular trash after you've emptied the contents into the cobalt chloride waste. Or if it's water, you can pour it down the sink. Then make sure you clean your bench before leaving. Contact me if you have any questions.